Hello, welcome to my video on data structures. This is part 6 of the hash table module. In this video, we will continue our discussion of alternative probing. Specifically, we will discuss the insertability of quadratic probing. With a little bit misuse of the word insertability, I mean we can always insert a new record into a hash table implementing quadratic probing. Recall the basis of quadratic probing. We are essentially trying to increase the step size for such an empty location quadratically with respect to the number of probing failures. For example, starting with the original hash value 9, one probing failure will lead to the step size of 1 square in the second probing. Two probing failures will lead to the step size of 2 square in the third probing. Three probing failures will lead to the step size of 3 square in the fourth probing, and so on and so forth. A question remaining for quadratic probing is that we do not know whether we can test all hash table locations. For example, consider a key value of 7 and a hash table size of 10. For the first 11 probings, we have only covered positions 0, 1, 2, 3, 6, 7, and 8. We have never been able to reach positions 4, 5, and 9. In this case, we may be better off with just simple linear probing that scans all positions one by one. To address this issue, we presented a theorem in the previous video. The theorem says that we can always insert a new record into a hash table implementing quadratic probing if the table size is prime and at least half empty. Note that we can easily ensure both conditions with table doubling. In this video, we will go over the details and prove this theorem. Okay, let's first clarify the notations and sort out the conditions for the theorem. We will use M as the size of the hash table and N as the number of records in the hash table. Since the hash table is at least half empty, we know that N is less than or equal to the floor of M over 2. For example, if the hash table has a size of 5, the maximum number of records it can contain is 2. Now, let's consider the worst-case scenario. First, in the worst-case scenario, the hash table is as full as we allow it to be. In other words, it contains floor of M over 2 records. Second, in the worst-case scenario, the probing keeps failing. In this case, we're interested in discussing whether different probings keep resulting in the same location. This is because if the answer is yes, then we might have an unlimited number of probings that keep ending in the same positions they are already occupied. Unfortunately, if you remember the example shown on the right panel, the answer is yes. We do have different probings ending in the same location. However, we may relax our discussion on the first few probings. As you can see in the example, there is no repeat in the first 6 probings. Now, let's consider how many unique probing locations do we need to ensure. Note that the table may contain up to floor M over 2 records. Therefore, we must ensure floor M over 2 plus 1 or ceiling M over 2 unique positions. In this case, based on the pigeonhole principle, we can guarantee that at least one position is empty. For example, we have 5 rooms and 2 are occupied. We must be able to access at least 3 unique rooms to be accommodated. Okay, now let's present the proposition we need to prove. If quadratic probing is used, and if the table size M is prime, larger than or equal to 3, and the table is at least half empty, then the first ceiling M over 2 probings must all end up with different locations. We are adding the condition M larger than or equal to 3, as M will be odd in this case, which allows us to express the number of records using floor and ceiling more easily. In practice, we will always initialize the table with size at least 3 to satisfy the condition. We will start the proof with two arbitrary probings, the ith one and the jth one. As I and j are indexes of the probings, they are both integers and non-negative. They also must be smaller than or equal to floor m over 2. This is because I and j are zero-based, and the range between 0 to floor m over 2 has contained ceiling m over 2 probings that are under discussion. We will prove the proposition using proof by contradiction. We will try to discuss the feasibility of the ith and the jth probing ending up with the same location. According to quadratic probing, it means that fx plus I squared mod m equals to fx plus j squared mod m. Here, fx is an arbitrary hash function that applies to the key x. And I squared and j squared are just the step sizes for the ith and the jth probings. After a series of simplification, we have I plus j times I minus j mod m is 0. Because m is a prime, we then have either I plus j mod m is 0 or I minus j mod m is 0. Note that the above statement is only true if m is a prime. Consider a counterexample if m is not a prime. 2 times 3 mod 6 is 0, but neither 2 mod 6 or 3 mod 6 is 0. Now, we need to discuss case by case to check whether I plus j mod m could be 0 and whether I minus j mod m could be 0. First, I plus j mod m cannot be 0. This is because I and j are not equal and are both non-negative. In this case, they cannot both be 0 and their sum must not be 0 either. For the same reason, they cannot both be floor m over 2 and their sum must be smaller than m. Taken together, their sum mod m cannot be 0. Second, I minus j mod m cannot be 0 either. This is because I and j are not equal and their difference must not be 0 either. The only possibility is that I minus j is m. However, this is not possible either since I is at most floor m over 2 and j is non-negative. Therefore, the difference cannot be m. Taken together, I minus j mod m cannot be 0. Therefore, since none of the consequences of assuming the ith and the jth probing ending up with the same location is possible, it must be that our assumption is wrong. In other words, they must end with different locations. Since I and j are arbitrary indexes, we can easily extend the claim to all probings. That is, the first ceiling m over 2 probings all end up with different locations. Lastly, from the claim, we know that among these ceiling m over 2 different locations, at most floor m over 2 can be occupied. This leaves at least one empty location where we can insert a new record. It then completes the entire proof. In summary, we have proved the insertability of quadratic probing. That is, we can always insert a new record to the hash table if it has a prime size and is at least half empty. In the next video, we will talk about universal hashing. Thanks for watching and see you next time.